I bought this fan, actually a lot of these fans, a year and a half ago. They might still be around. They're decent. It's not a review about the fan. I'm more interested about the control of the fan. What I wanted to do was just throw it on the scope and see how it's actually controlling the fan speed. My guess is that it's probably pulse width modulation, but it has this one feature that I really did like, which was this potentiometer that allows you to do what they call stepless speed control, where you can control the speed with seemingly infinite resolution. Reminds me of various things that have this kind of control that would be AC, that would be like a dimmer switch that use, either wave chopping or variable frequency drive, but we're talking about DC. This thing is powered by a USB cable and it's 5 volts. I needed to clean it because it looked disgusting. I have a blue one. I don't know why I didn't use the blue one for this video, but I picked the white one so you can see some of the grossness that's still on there, but it's much, much better than it was before I took it apart and cleaned it. If you have one of these and the fan blades get really nasty, you can gently pull the entire assembly out. You want to pull it out as straight as possible because the bearing is right there. And if you're not careful, you can damage that bearing. And you don't want to get that wet either. You want to keep this as dry as possible. So when you're cleaning it, try to cover this up with something to keep moisture from getting inside of it. Well, what you can see here is a pretty common configuration, which is there is a fixed magnet in the rotor. This is the rotor, and the stator is a 4-pole configuration. And I can see 2 wires coming up here, which means I believe, actually it may just be 2 wires going to a controller that's on that board, and it does all the commutation stuff. I'm going to take apart the bottom of this and see what we can get access to. There are 3 little sticky pads. These have screws under them. They do, and they're just Phillips screws. They are sticky pads, so it's not like it's a plug or anything that you can easily put back in again. So I'm going to pull these 3 off, and then we should be able to access the bottom of this. Just need a regular Phillips screwdriver. Kind of nice. I'm taking this off and I see, oh, look at that. There we go. There is a little USB connection on the back here for micro USB. And all that has is just traces that go to a plug. Looks like a JST connector. That goes over to here to the circuit board. But I don't think this is the main board. This is just like the power and control input board. Meaning, what I see here is a potentiometer. I see a little 6-pin IC. It looks like a power supply, and I think that's about it. What it's doing is it's taking the 5 volts and it's perhaps just using this potentiometer to vary the 5 volts to the fan itself. It actually may not be PWM'd. Let's get some clips onto the wires going onto the fan, which there are 2. It just says F plus and F minus. This wire is enamel coated, so it's going to be a little tricky to get a connection onto it. Let's get the fan back in there. It's got quite a range, but there is a bit of a dead zone at the end where it won't go any lower. And then right about there, before it clicks off, it just stops. So I'm going to let it run on its lowest speed. Okay, that's on there. Cool. Hope that stays on there. We'll go to fan, positive, and I am going to just put it in auto ranging mode just to get us something. Hopefully it gets us something. It is. Whoa. Look at that. Okay, so I can't pick up a frequency there, but when I increase it a little bit, you can see the frequency climbing to 696, 670 hertz. So let me auto range it again. Damn, my hand's gonna be in the way. Yeah, it's not doing the best job of determining. I think it's too noisy of a signal. I do want to see if I can set up an offset here. So it's not going to drop to 0 because it's got a big capacitor, 16 volt capacitor. But it looks like what they're doing is they're setting up a boost converter, going from 5 volts, I think it starts off at. Yep, 4.778. And the reason why I can't determine a frequency, I just noticed this. It says frequency question mark, time period question mark, is because at this point, when it turns on, the input voltage is 5 volts and the output voltage is supposed to be 5 volts. So the boost converter is basically off. There's no switching going on. But when we start turning it up, that's when we start getting the frequency changing. So you can see 136 kilohertz. It might be a fixed frequency, and it's just what duty cycle is it at. But you can see the voltage increasing up to about 8.7 volts. Actually, it actually went out of range there. I thought you might see the actual motor controller on the fan modulating, but it seems like it's just way easier just to give it a variable voltage and the standard controller on these fans, because the motor has a controller on it as well that's monitoring all this and doing whatever it's doing. It's harder to get inside of that. Might be a separate video, but I wanted to see what was going on with these stepless control where it has a potentiometer. So let's offset to move the channel 1 vertical scale, move it down. And then what we can do is change the volts per division down to, let's go back to channel. Volts, vertical scale, 1 volt per division. Oh, there we go. Offset it again to get it right around the 0 crossing so we can keep decreasing. Oops, this is what I want. 2 volts, 1 volt, 500 millivolts. Let's see if we can get it to come down there. There we go. Oh, look at it go. So if I can get the trigger then right in there, we should be able to see it. Oh, look at that. Come back to the horizontal. Let's horizontal time base. There you go. Getting a bit of aliasing here because we are down to, we're at 500 millivolts and 500 million samples a second. But if we, yeah, oh, we went out of our trigger window there. Let's just get it right in the center there. But if I mess around with this, you can see, yeah, now it's showing the frequency at like in the megahertz range, 5.5 megahertz, 8 megahertz. I would think that the switching frequency would be a little bit lower than that, but let's get it in. Yeah, it's kind of bouncing around a little bit, so I'm not sure if it's really getting the, yeah, we're getting some kind of funky aliasing there. Right where we're in the noise band, but you can see those pulses, and that's the inductor dumping into the capacitor. There's an inductor on this board right here, and then there's the capacitor, the reservoir capacitor, and that inductor, as all boost converters do, dumping as the MOSFET shuts off, and probably that's built into the little 6-pin chip, or maybe there's a separate one. Oh, that might be one right there, right here. Well, when it turns on, it allows the inductor to build up a magnetic field, and then it shuts off. That magnetic field collapses, and it dumps current into this reservoir capacitor. And that's what we're seeing here. Whenever you see these spikes, we're seeing that voltage increase. And we're talking, I mean, we're at a 500 millivolt scale, so we're at about 100 millivolts per division. So the peaks are, maybe we're talking 200 millivolts, 250 millivolts. And there could be a little bit of aliasing there. If I maybe decrease the time base down a little bit more, because that is a lot. So if we could go to there, just get a couple of them on the screen at the same time. The frequency is bouncing around a bit. 6 megahertz. Let's see if we can get the trigger a little bit higher up there and see if it stabilizes a little bit more. Or if we get it right in the middle, see right in the middle there is that noise. And we're getting some aliasing. Yeah, we're getting some aliasing there. There we go. See if it stabilizes. I should probably also note that I have this thing plugged into a battery bank that is powering 3 other things. So you might be getting some common noise as well. Let me move this to a separate battery and see if that perhaps reduces the common noise. In just a moment. Okay, so I have played around with this a bit, and I've got it on a separate battery from the other supplies. I have this fan connected on its own battery. A lot of noise. It sort of makes sense. This is on a battery supply, so the battery itself is bucking the voltage down. I could use a switch mode power supply, but then you're still going to get noise from that. So it's a little difficult to kind of get a super clean, quiet signal, but this is pretty decent, I think. We're at our lowest voltage here. I think we're kind of seeing actually a little bit of a combination of the ripple coming from the 5-volt USB supply. What is the output going to the fan motor? So what I wanted to show here is that on the battery itself, on a separate battery, this is definitely a quieter signal than it was when I had it plugged into a battery that had everything I'm doing here is solar powered. So like the lights and the camera and all that stuff is all plugged into a battery that's been charging via solar. So I realized, oh, that's a lot of stuff being plugged in and a lot of noise on one source. So again, we're talking in the millivolt range, but it's detectable when we're playing around in the millivolt range. But what I've discovered probing the output of this little circuit here is really just variable voltage. It's just setting up a potentiometer to the boost converter and allowing that to function as a variable voltage supply, and then that gets fed to this little 2-wire connection to the fan. And if I turn the fan off, I'm just going to remove the fan blades again. Actually, do I need to do that, or can I get to this in the back somehow? There is a little cap on the back. What I wanted to try to show is that little motor controller, and I'm wondering if it is potentially behind this little cap, because there's got to be screws holding this thing in, and there's the back side of it. Well, that didn't get us very far. I thought there were screws here, but there are not. It's just the back side of a circuit board. So if I flip this around again one more time, remove the fan blade. Don't recommend doing this a whole bunch of times, but there's a central core, like a plastic core. What if that's glued in? This maybe just slid down onto that central plastic core, which you can see starts in the back here and it protrudes out. And I don't believe that this is going to want to come off of that. Because, I mean, if it wasn't glued down and it just kind of sat in there, it might generate enough torque. Because this is a pretty torquey motor. It might rotate this, and then you don't want this thing torquing and turning when it turns on instead of the fan blade. But there is a controller down there that is controlling this commutation. And I potentially could get the... And I can't get in there without the fan. Without the fan, this is not going to work. I mean, I could get maybe a loop of wire. I could wrap it around. I don't think that it's allowing it to do anything. Let's get out the USB power analyzer. Because if we have no power going in, then it knows there's no fan blade there. And it is not going to try. Oh, it is. That is. It's putting 6 watts, 7 watts, 8, 9. But then it's cutting back right away. 1, 4, 6. It's trying to commutate, but then not. It's detecting there's nothing there. So we're at 1.9 watts. And then let's see what we get if we crank it up a little bit. It tries to go up to 9 watts. It's hanging around 9 watts, but it's just not. It's showing an applied voltage, but I don't. There we go. There we go. Oh, awesome. Awesome. That's so cool. And now I'm going to back down the potentiometer. And you can see that it's backed off, and it's just kind of staying at a more steady rate. Now we can't trust any of the voltages we're seeing here because it's just a loop of wire. All we're doing is just getting a crude representation of what the waveform looks like. Let me try to trigger on that a little bit more. Not a little bit more. Let's try to trigger it all on it. And there we go. And let me get the horizontal a little bit more. The temptation to get the thermal imaging camera out, but there's not, a need for even more stuff. But let me get the horizontal a little bit widened out. We're seeing the stepping. Yeah, we're seeing the stepping, but we're still getting... Let's decrease our time base a little bit. And you can see where it's trying to drive. Again, this is not a great way to do this, but it gives us something. It gives us something to look at. Let's get this too many waveforms. Looks like 3 would be good for here. Let's get our trigger just a little bit more. Remember, we're at 1.2 millivolts. We're very low voltage. But if I increase the speed, you can see it trying to apply a voltage, and then now it's pulsing. And that's to keep it from overheating, which is pretty cool. So you're seeing that pulse. And if I widen out even further, really wide. Yep, now you can see it as it scrolls across, that it's trying to start, and it's delaying in between. It's pretty cool. If I back it off, what do I get? I might go to a continuous pulse. It's allowing it to run longer. See, it's going longer, 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 longer. And that may just run continuously. Now I'm all the way down to basically the end stop before it turns off. If I turn it off, now it's just off. Still some noise there because we got an antenna. But yeah, if I turn it back on again, and crank back up with no fan blades on, it's pretty cool that this thing, I mean, it has lock rotor protection, which is pretty neat. Meaning if you stop, the fan blade stops, it's not going to just overheat. But there it is trying to commutate. It's got a delay in between to keep itself from getting too hot. And I mean, we're looking at about 6.6. The USB analyzers can be way slower than what you're seeing on this scope. But that's pretty slick. That was way more than I was expecting to be able to get out of this. So cool stuff. I'm going to get this thing off of here now, and I'm going to turn off the fan. That's warm. Can I get the thermal imaging camera on there? Okay, so that was a bit unexpected. As you can see in the video here, there is not much heat on the windings. But what I didn't realize is that there is that motor controller chip that is down here. I think it's the Hall effect and motor controller chip all together as one. And it gets hot. It gets really hot because it's pumping out a lot of current into these windings, and there's a lot of mass here, but not much here. So it seems to have temperature protection because it gets up to 100 degrees Celsius, about 100 and 102 on the thermal imaging camera, and then immediately starts modulating itself at that temperature to not exceed it. Well, let's wrap this up. I'll just put the fan back on here. Oh, is it turned on? Hopefully it's not. No, it's turned off. It's low voltage, so it doesn't really matter, but I'd rather have it not start spinning while trying to put it on there. But it should start. Yeah, the battery turned off. There we go. It's fine. But just to show you, I don't know if this will show up on the scope, but this does have lock rotor protection, which means if the fan if you stick something in the fan, your finger, whatever, or any implement, it won't just keep driving the fan motor until it burns up. It will actually stop operation and protect itself, which is pretty cool. So let me get back on here. So I'm recording here, and then I get our time base a little larger. If I start slowing the fan down, do I get... Yeah, you can kind of see that the power supply gets a little bit wonk. But we're not seeing... I can feel it trying to start. No. If I try it at its highest speed, we'll go there. It kind of hurts. There we go. Yeah, you can see it trying to start. You can even see it with the fan blade trying to turn. And then yep. So let me widen out the horizontal a little bit more. There you go. So now we're seeing the same behavior on the power supply side as we did across the commutator, which is pretty slick. And that same part is probably getting just as hot as it did with the fan blade off, because it doesn't, when you stall the rotor or stopped the rotor, the behavior is basically the same. Okay, I hope you enjoyed taking a look at just fan speed controls in different ways. It's different than I expected it to be. I thought perhaps this would be more, honestly, I thought it'd be more complicated and would actually interface directly with the motor controller. But again, seeing how inexpensive a fan like this is, this motor and its control is something that probably has already been spec'd out and then it has a speed that it'll operate at, and then you just provide a voltage to it, and then it will commutate at whatever speed range it wants to. So it makes sense after opening this up that, oh hey, this is probably the much simpler way to do it. Just give it a range of voltages. And so all you got to do is basically create a boost converter that allows you to operate between, say, 5 and 8.5 volts, or maybe 9 volts, give or take. There's your speed range. While it does say it's infinite step, it's not really. It seems like it might be, but basically this is a voltage divider that's being read by that chip, and there's some sort of analog to digital conversion going on that's going to set up some particular voltage. That's it for this video. If you like what you saw, please like and subscribe, and I will see you in the next one. Take care.